Hi. Okay, so I want to prove this theorem that we mentioned in the past couple of videos and also at the end of class on our last in-person day. And let me say that so I am going to show you the proof so that you can believe that it's true. But at the end of the day, what we're trying to do is going to be finding these so-called standard matrices. So I'll recall what that means in a second. But all this to say, I am going to show you a proof, and by proving it, we will learn how to find the standard matrix associated with a linear transformation. But then what we actually need to do will just be to find that or those standard matrices. Okay, so we have this theorems. A transformation T from Rn to Rm is linear if and only if there exists a unique matrix A such that T of x can be written in this form A times x. So we sort of have two properties going on here. And the first one I'm going to say is this property of linearity. So let me call that property 1. And the second one is that a transformation can be written in this form as a matrix times a vector. And we have this if and only if statement here. So this is saying a transformation is linear, then it can be written as a matrix times a vector or times the input vectors. So, but it's also saying if it can be written as a matrix times a vector, then it's linear. So that's with that if and only if. It kind of means 1 implies 2, but 2 also implies 1. If it just said if, then that would only mean 1 implies 2, not necessarily the other way around. And so we've seen this in class, but let me just kind of recall it here. We can also notate if and only if by IFF that we've seen, but also this sort of double arrow. And we've seen the arrows, I think, before. I can say something like 1 implies 2, meaning if it's linear, then it can be written as a matrix times the input vectors. But also, I can say 2 implies 1. And hence this double arrow here. So here's sort of one half of the arrow and here's the other half. And if I want to prove that this is true, then I need to show that both this and this are always true. Okay. And this second thing here, saying that if a matrix can be written in the form T of x is equal to A times x, then it's linear. We've talked about that in class, but not explicitly shown it. And so when we prove this, I'm going to start with that since it's most familiar. So in order to notate that, so this is the one right here that I'm showing. So let me draw this backwards arrow. And I'll say that this is common practice in mathematics. If I have an if and only if proof and I want to show both pieces, I'll indicate which one I'm doing with the arrow. And so what that means is I am supposing the second statement is true. So suppose that my transformation T of x is of the form A times x for a matrix A. What I need to do is show that this implies my transformation is linear. But what that means is we must show that for all input vectors, so I'll say u and v in Rn and constants, c and r, just r, we had these two properties that we mentioned. So I need for A times u plus b to equal A of u plus A times B, that's property 1. And property 2, I need to show that A times some constant times my vector is equal to that constant times A times my vector. And we've seen these two properties before with t's, but since we know t is equal to A times x, I can just go ahead and write it as matrix multiplication. And lastly, I am going to denote the columns of A by the vectors A1, A2, up to AN. Okay. And if I want to show that this is true, I'll just prove these two things one at a time. So first, property 1, if I have that A times U plus B, I want to show this is equal to A of U times, or plus A of B. So let me just see what happens. So if I have A, my matrix A, times two vectors, remember from the last video, what that means is I am going to multiply the first entry of my vectors. So that would be U1, say, plus B1. And remember, these are entries in my vectors. They are not vectors themselves. And I'm going to take that and I'm going to multiply it by the first column of my matrix A. So that would be A1, which is a vector. And I'm going to go through and do this for all columns, eventually ending at the nth column. So here I would have my nth entry in my vector U plus my nth entry in my vector V, and I'll take that and multiply it by the nth column of A. Okay, and now I can use these rules of scalar and vector multiplication to distribute. So what I can do here is I can say, well, this is the same. This is just some constant or some scalar. This is the same as doing U1 times the column A1 plus B1 times the column A1. Put that in parentheses. That's just me distributing this vector to both. And I can actually do that for each of my columns. And so I end with UN times AN plus VN times AN. And here, let me separate out the terms that have U's in them versus the terms that have V's in them, and then collect them accordingly. So this is the same as taking U1 times A1, maybe U2 times A2 if I had written that, all the way to UN times AN. And I can do the same thing for the V's. So I would have B1 times A1 plus Bn times An. But notice here, this is just my vector U times my matrix A. So I have, and let me write it instead of saying U times A, this is just A times U. And similarly, this is just my vector V times my matrix A, and this is exactly what we wanted. Okay, so that proves property 1, and now I need to prove property 2. So So property 2, what I want to show is that if I have A times a constant times U, that eventually I get that it's a constant times my matrix A times U. So if I do that, I'll use the same trick as before, and I'll say that this is just my first entry in my vector U, so that would be C times U1, where both of these are just numbers, times the first column of A. And similarly, I would have C times U2 times the second column of A, all the way down to C times UN times the nth column of A. And from here, I can rearrange these a little. So let me first factor out a C from each of these. So I have C times U1 times A1 plus U2A2 plus UNAN. But notice this here is exactly what I would get if I took my vector U and multiplied it by A times A. And just rearranging, because multiplication is commutative, this is actually equal to C times A times U, which is what we wanted. And so what this proves is that if my matrix can be written in the form A times any input vector X, then it's linear. So this proves that 2 implies 1. Okay, but next, what I need to show is that 1 implies 2. This was this forward direction, meaning that if my transformation is linear, then I can write it in this form A times X. And so this is what I want everyone to really pay attention to and think about as I'm going along, because this is going to show us how to find that special matrix A, which is going to be called a standard matrix. Okay, so first we're assuming, suppose T is linear, and we want to find some matrix A so that T of X is equal to A times X. So that's what we want to find, is this matrix A. So to do that, remember that we had these standard basis vectors, or AKA the E's. So let this collection of vectors E1 to En be the standard basis vectors of Rn. And remember, kind of off to the side, and I'll erase this in a second, that E1 was equal to 1 in the first entry, zeros in all the others, and E2 would have had a 0 here, but a 1 there, and so on. Okay. All right. So I have this collection of standard basis vectors, and one thing to notice is that if I have some vector x in Rn, I can actually write it as x being equal to this matrix where the columns are the standard basis vectors, times x, which by definition is equal to the first entry in my x vector, let's call it x1, times the first column in this matrix E1, plus all the way down the nth entry in my vector x times En. And notice here, if I am taking the first entry in my vector x and multiplying it by a vector that looks like 1 with a bunch of zeros, then that's going to be equal to just x1 with a bunch of zeros. Similarly, if I were to take x2 times E2, then that would be equal to x2 times 0, 1, a bunch of zeros. And I'd end up getting an x2 in the second position, and so on. So it's clear, hopefully, not really with this picture, but it's hopefully clear that if I combine these, I'll end up getting x1 in the first entry, x2 in the second, x3 in the third, and so on. So this actually is equal to x. It's just a more complicated way to write it. But what I'm going to say is that we can use these basis vectors to find that standard matrix A. Okay, so let me erase this kind of scratch work at the bottom. All right, so let's see what happens when I have a transformation, a linear transformation, and I apply that transformation to some random vector x that we now know can be written in this different form. So I'll say that t of x is equal to, so I have x here and I have this here, these are the same, so that's equal to t times x1 times e1 plus, and let me write the second entry here, x2 e2 plus xn times en. And normally we don't know what we could do from this spot. But remember, we're assuming that our transformation is linear. So we can say by linearity, this is equal to, and now I can take this t and I can apply it to the first vector. This is a vector, and the plus t applied to the second vector, and so on. So I'll write that t of x1 e1 plus t of x2 e2 plus t of xn en. And again, because these are linear, or this transformation is linear, and all of these x's are just numbers, I can pull them out using this second property of linear transformation. So this is actually equal to x1 times t of e1 plus x2 times t of e2 plus xn times t of en. But notice this right here is a vector, this right here is a vector, this right here is a vector, and I can collect all of those vectors in a single matrix, and they're all multiplied by these constants, aka the vector x. So another way to write this is as the matrix t of e1, t of e2, all the way down to t of en times my vector x. And so anytime I have a linear transformation, I can write it in this form where this right here is going to be called my standard matrix. And what we'll see is that anytime I have a linear transformation and I want to find out what the standard matrix is, I can just find out what happens to my standard basis vectors. And that's the really important thing that we want to take away from this proof. So maybe I'll put a star here because the standard matrix is what we're going to want to be able to find out. Okay, so that proves what we wanted. So here this proves that 1 implies 2. But I'm going to say that actually we're not quite done. And let me go back up here to this statement of the theorem. And it's that there exists a unique matrix A. And so actually, let me put a question mark here. Not quite. So we still need to show that A is unique. Okay, but again, this thing that I starred, that's what we're going to need to know. But if we actually want to believe that what we're doing is creating the only matrix, we need to prove this property of uniqueness. And the way to do that is to suppose that there's some other matrix, let's call it B, such that T of X is equal to B. So let me suppose this transformation of X is equal to some other matrix B times X for some, say, M by N. Remember, this is a transformation going from Rn to Rm. M by N matrix B. And let's say, so where B is not equal to A, where B is not equal to A. And if that were the case, then I would have two matrices that achieve what we want, which would mean that this matrix A, this thing that we're defining as a standard matrix, is not unique. And so what I'm going to do is I'm going to actually show that this matrix B must in fact be equal to how we defined A, which would mean that they're not different. Okay, so let's do the same thing we did above, where I let the columns of B be represented by the following. So let B1, B2 up to Bn represent the columns of B. And what this means is the first column of B, say B1, is equal to the first column of A, which is T of E1. Okay. Actually, let me say that a little differently. Sorry, this is totally the spot where I would end this, or I would have started this video over, but it's already gone on so long. Okay, this is what we want to show. I'm going to claim that B1 is actually equal to this T of E1, but let me actually prove that. So, okay, I have this matrix. Let me cross this out. Sorry. Actually, I can erase it. So there's no evidence that it ever happened except in the video. All right. So what I want to notice, I'm going to show that this B1 is equal to this T of E1. So here, if I take the transformation of, I'm allowed to put in any vector with n dimensions. So let me put in this vector, the standard basis vector E1, which we know is our first column in A. So if I do my transformation, up here I just said that my transformation is equal to B times X. So if this is acting like my X, then this is going to be equal to B times E1. But this is equal to B times this vector here where it's got a 1 in the first entry and zeros everywhere else, which means that this is going to be equal to just the first column of B, which means that the first column of B is equal to the first column of A. And I can repeat this process n times to see that, I'll say, maybe see that all n columns of A are equal to the n columns of B, which means that B equals A, and so they're the same. This means that A must be unique. And that proves 1 implies 2 and further proves the theorem. So put an X to show that we're done. All right, but again, this standard matrix definition up here, actually just this part, is what we're going to be interested in terms of defining linear transformations, no matter how they're given to us with matrices. And so we'll look at another example of that in the next video.